Hello, F Sharp, and we are back, continuing our journey of writing a optimized dictionary. Specifically, what we are going for is a very fast read-only dictionary. That was my original motivation for doing this work. Maybe at the end, I'll talk about how to add some functionality to make it a proper dictionary with the ability to remove values from it, but that's not my primary concern right now. Now, where we left off was the completely naive implementation of a dictionary. And what we're seeing on the screen right now is the benchmark results for that. And what we see is that it is far, far slower than the dictionary that is built into .NET. Now, the first thing that we want to attack, though, is the allocation. So over here on the right side, we see we have quite a bit of Gen 0 allocation going on. Now, why is this a problem? Right now, what we are benchmarking is just the getting an item from the dictionary. Specifically, what we are doing for each of these points is we are generating 100 random dictionaries, and we're performing 100 random lookups on them. And the idea with that is that we don't want to tune our benchmark to a specific set of keys and values. We want to randomize it. We want a good sampling of the different access patterns so that we're not tuning to a very specific set of values. And so the fact that there's any allocation happening while reading a value from a dictionary, while looking something up is, well, to be honest, absurd. It is horrendously terrible and should not be happening at all. So before we even really concern ourselves with trying to tune this, we need to get rid of any allocation that's happening inside of our code. And now, one thing you might try to do, and I'm going to flip over to the code here real quick, and I'm just going to go over real quick what we're looking at. We are, actually I had that open to the correct thing. So this is the version that we're looking at. I'm in the fast dictionary test solution. I'm in the fast dictionary test project, and I'm looking at the naive dictionary implementation. And inside of here, I have my add entry code and my get value code, and I have logic for resizing. And then I have my method down here for actually, looking up and getting the item. Okay, so somewhere in this get value code, so here's the method, right? Item with get, I pass it a key and I say, hey, give me the value for this. And this is calling the function get value for this class. And this is the code that's then running where it's computing a bucket index for that key. So it's like, hey, which bucket in this backing array am I going to go check? And it looks that up, and each of the buckets has a reference to an F# list, and then searches that list for an entry and returns the value that's in that entry if it finds something that matches. So somewhere in here, there's allocation happening. We want to get rid of it. Now, we could kind of guess at it. Well, hey, where do we think this is happening? And I know where it's happening just because I have experience writing this and I've run into this problem before, but I want to show you how to be able to diagnose this yourself so you can find it. And the tool I actually ended up using, and I think gave the best visualization, is a tool called Superluminal. Superluminal, this is the result of running it, and I can actually start up another instance. Superluminal is this great application. An individual license for it cost €59, I believe, is when I last checked it. And it's a tool by the people who created Horizon Zero Dawn, I believe. And so these are game devs, hardcore performance people. And so they made this tool for doing profiling of C++ and .NET, which is fantastic. And it works with F# relatively well. I mean, it's not designed with F# in mind, but it works pretty well for our purposes. And so what I did is I say like, hey, this is the application I want to run, which is my benchmark application. and I give it the working directory and I say like, hey, I want you to profile this and I want you to benchmark naive and I want you to do many iterations. And I'm going to come back to my code so you can kind of see what it's doing. So we have the benchmark command line project, and what it's doing is I have the entry point and I'm passing in these arguments and I'm using argue to kind of parse those arguments and saying like, hey, I want you to benchmark. It then benchmarks and does a match on the string. And in this case, it's saying like, hey, I want you to run the naive benchmarks. Well, in this case, so this is what it would do if we were running the benchmarks. If, on the other hand, we wanted to profile, which is what we're going to be doing now, is say like, hey, go figure out what method it is that we want to run, get the number of iterations, and then what it does is it calls the profile function. Let's look at what the profile function is. So I'm hitting F12 on this to follow it. And again, it kind of matches on, okay, which of our different dictionary versions do we actually want to profile? In this case, we're passing the argument naive. It creates an instance of our naive benchmark class, and then it just runs that test over and over and over and over again so that we can get essentially kind of get burn in so that we get the most optimized version that the .NET runtime will produce. And we get a good idea of like, okay, how fast is that with the best possible code? So I'm telling Superluminal, hey, go run this and give me the sampling information and analyze it and tell me what the result is. And so I'm going to jump back over here. So I could then say just run and it would go capture a bunch of data and it would run for a little bit. But I've already run it. So I don't want to waste your time. And so it's going to produce a visualization that looks like this. And there's more detail than we necessarily need in here. But essentially what you're seeing here is all the different threads from our program. And a lot of these are things associated with the .NET runtime. So stuff that we don't actually care about. This is ours, right? This top one is the one that we care about. And so what I'm going to do is I'm actually going to expand this thread and I can see, I can kind of see this flame graph of all the stuff that's happening inside of here. And so what I want to do is to say like, I'm going to just kind of like focus on an individual run here. And so what I'm going to do is I'm going to say like, hey, go ahead and let's zoom in on this section and say, hey, what is the hot stuff in this section? And the reason I'm ignoring all the stuff at the beginning is this is like the constructors, the program starting up, it's creating the instance of our benchmark class. And so it's not actually running yet. So that's why I wanted to look at, the code actually running. So this is when our method is being called like over and over and over and over again. And when I highlight that section, I say like, hey, this is what I'm actually wanting to look at. It then gives me some additional information down here. It gives me a call graph. I could also look at the function list or the thread interaction, which in my case, I don't really care about. So I care mostly about the call graph. It gives me this nice pie chart of where I'm spending my time. And then over here on the right, I can see kind of the source disassembly. So if I want to see the raw x86 assembly, I can see that, which we're not there. We'll get there, but we're not at that level of optimization yet. So right now, what I'm going to do is to say, hey, I'm going to right click on it and say, hey, expand hot path. And this is just going to expand out all the function calls and what is spending the most time on. And I really like this right here, this inclusive time. And right now it's the % of time our program is spending in this method or function. And what I'm going to do is I'm going to click on this, which is our V2C. This is fast dictionary test benchmark naive test. So this is the method it's calling over and over again for us to profile. I'm actually going to right click on it again. I'm going to say, set this as root. And say like, hey, I want this to now be the root of the call tree that I'm analyzing. And it's because I don't care about all that additional stuff that the .NET runtime is kind of wrapping my program in. I'm really only concerned about this piece. So I've zoomed in on it. And I'm going to say like, hey, go ahead and expand the hot path. And this is kind of giving me a nice breakdown of like where are you spending all of your time? And there's a couple different things that we should start observing here. First, list module.find. We are spending 55% of our time in the find function for the list. Okay, where is that in our code? And I'm going to come back here to naive, and it's right here. We're spending a lot of time in this list.find function call. Why are we spending a lot of time in this list.find? Well, if we look inside of it, what is happening inside of it? We're saying, okay, well, we're making calls to the Microsoft F# core language primitives hash compared generic equality object. Okay. So what is that? There's kind of two things I want to emphasize here. It's using F#'s default equality code. And I'm trying to think of like the best way to say this without sounding mean, but F#'s defaults are safe. So it's very easy for a new programmer, someone brand new to development, brand new to writing software to kind of pick up and like get the behaviors that they're expecting to get because F#'s defaults are safe. F#'s defaults are not fast necessarily. Sometimes they are, but if F# is going to default to something, it's going to default toward correctness and safeness. It's not going to default towards speed. And so what we're seeing here is the overhead, I'm kind of doing that in air quotes, of that defaulting to safety behavior is like, hey, code that's robust for doing this generic equality comparison is not necessarily very fast because it has to deal with every possible situation. And we're seeing that overhead. The other problem that we have going on here, and so it can be creating new instances of these comparers all over the place. And this is where our allocation is coming from. Because when it's doing these comparisons, that comparer is a new object. That new object is getting allocated on the heap. So that's why that default behavior, that default equality checking is causing us to be slow because it's doing lots of allocations on the heap, and that's going to incur the wrath of the garbage collector. And so we would rather avoid that. There's another thing I want to point out here in this code is if we go and look at the list.find function, like how is that actually defined? I'm actually going to hit F12 again, and this is how the F# core libraries define find for a list. What you find here, there's two things. First of all, this is recursive, and so it can call itself. And what that means, there's kind of two implications here. Recursive functions cannot be inlined. And so one of the biggest performance boosts that you can get to increase the speed of your algorithms is to inline really small functions. And that means when you do that, you don't need to create another frame of your call stack. And we're not there yet, but that actually ends up being one of the big things slowing us down later in this. And so recursive functions cannot be inlined. Inlining is one of the best performance optimizations that you can get. And so by using list.find, we've eliminated our ability to get that additional boost in performance. Also, this predicate is a function that's being passed in, and it is not being inlined either necessarily. There's a thing that's been added to F#, a hint, which is inline if lambda, which you can use for something like this. And I don't think this is going to allow me to edit it. Yeah, no way it's going to let me edit it. That's fine. But we can provide a hint to these functions saying like, hey, I'm going to pass you a lambda, and I want you to inline this lambda, which again is another way of eliminating a frame for a call stack. And we don't have that here. So list.find is a very slow way of kind of looking up these values because like we're precluding ourselves from being able to do any kind of inlining. That's a problem. So this is slow. Another place where we're having to do hashing stuff, and I'm going to see if we see it here in Superluminal. Yeah, we got that problem. So list.find, that is incurring a whole bunch of these hash compare language primitives from F#, but we will also notice we're just seeing that in the naive.test method as well. Like, hey, inside of the test method, we are still creating these generic hash compares. Where is this coming from? That's a good question. I can tell you where they're coming from. They are coming from here. So we're computing this bucket index here. So we want to get a value. And the way to map a key to a bucket in a dictionary is you take that key type, you compute its hash code, and then we take the hash code and map that down to the individual bucket in our array. And that's what this function is doing, this compute bucket index. Because what it's doing is it's saying like, hey, give me the hash code for this type. And then it has a logic for mapping that down to a particular bucket in our backing array. This hash function is the F# generic hash function. Again, this is the safe defaults that F# gets you, which are great. So don't take this in any way as me like deprecating F#. F# is a fantastic language. I love F#. But we also need to be aware that F#'s defaults are not necessarily fast. So when we are wanting to write fast F#, we're going to start writing a slightly different style of F#. So this call to a hash function to do this generic hashing, this is also causing these instances of hash compare to be created and used. And so we want to get rid of this as well. So we kind of now have two different targets for which are causing our allocation. So how do we get rid of them? That's a great question. So I'm going to go ahead and jump to our zero allocation version. So I'll go ahead and close this, and I'm going to put zero allocation on the right so we can kind of see these side by side and compare them. So on the left, we have our naive version. On the right, we have our zero allocation version. And I'm going to zoom out just a small amount. So what's changed? So before we had this compute bucket index and it was using the generic hashing function for the key. Now what we are using is equality compare.default.get hash code. Why are we using this? Well, this is saying, hey, .NET Runtime, give me the default hash code logic for that. And what's great about this is that if it's a struct, if it's a value type, the .NET Runtime knows how to inline this method call. There's special logic in there. So if this is a struct, it knows how to inline it. And so this is going to give us the best possibility, close to it, but this is going to give us a much faster version of the get hashcode method for this type. So that's the first thing that's changing. The second thing that's changing is that we are writing our own loop for iterating through the list. And the reason we are doing that, instead of using the list.find over here, we're not using that anymore. We're using our own loop for recursively going through the list. We compute the bucket index. We get the bucket that we're interested in. So this is going to be the list that entry into the array is pointing at. And we say like, hey, loop through that list. And, oh, sorry, this is adding entry. My apologies. We're looking here. We're looking at the get value. My bad. So we compute the bucket index, which this is the list that our entry could possibly be in. And then we say like, hey, loop, go find the value that I'm interested in. And so instead of using the list.find function, we're using our own loop. It's still recursive, so it still can't be inline, so it's still not as good as it could be. But instead of using that generic equality, we are now using the equality compare.default.equals. So this can possibly be inline now, and it shouldn't allocate memory either. So these two changes should hopefully get us away from having to allocate any memory while we're just doing a lookup in our dictionary. And again, I went ahead and already ran those benchmarks. And so this is the result when we run our zero allocation version. Now, what you might find interesting is like, wow, huge performance improvement. Our zero allocation dictionary for a 10 element dictionary where the key is an integer is same performance as the .NET dictionary. Now, it is slower when we have 100 integer keys, still slower for 1,000. And wow, it seems to be pretty quick for 10,000. Like, what's going on here? Oh, where is it? Cache hits, man. We're going to talk a lot about cache misses and cache layout layer. So I'm not going to go into the depths of like why exactly is this happening. Basically, well, okay, I'll tell you. Because an F# list is a linked list, each of those elements is an individual object on the heap, and those objects could be spread out anywhere on the heap. And so an F# list, a linked list, is possibly one of the most performance antagonistic collections that you could possibly come up with. So that's kind of what is going on here. We'll fix it. That's why this series is going to go for a little bit. But again, we also see here for our strings, the performance is still not nowhere close to the .NET dictionary. Well, I guess it's closer here, but still we're a ways off. The good news is that pretty much all of the allocation is gone. We still have some here. I'm not exactly sure exactly why we're allocating 1 byte here. I was never able to actually narrow that down, but fortunately in future versions, that's all going to go away. But this is essentially 0 compared to what was going on over here, which was absolutely absurd. So massive improvement. All of our allocations are essentially gone at this point. Our performance is better, although erratic, but we'll work on it. We're now somewhere in the ballpark. And so hopefully that single step is helpful for you, and just like an awareness of, if you're going to be doing equality and hashing in F#, be very aware of how you're doing it, because you may be incurring a whole lot of allocation that you weren't aware of. So until next time, thank you very much for spending some time with me. And I look forward to showing you the next part where we continue to take this performance even farther. And so thank you very much for spending some time with me. Have a good day. Bye-bye.